Okay. I think it's been 10 minutes since I started the break. Okay. So I'm going to finish off Chapter 8 with Section 8.8.2. Now, Section 8.8.2 is just called Other Problem Types because really there's two different types of problems in here. They're somewhat related, but not that much related. So one type of problem in here are velocity and flow rate problems. If you have a river which has a rectangular cross section with width 10 meters, depth 5 meters, if you know the velocity of the river, right, how fast the river is flowing, it might be flowing different speeds at different depths. How can we find the rate of flow of the water? How can we find how much water is flowing? How many cubic meters per second of water is flowing? Is there anyone here who feels like they know how to approach that? Anyone? How many people here have never seen a problem like this before? Is there anyone who's seen problems like this before and doesn't really know how to approach it? Okay. Is there anyone here who remembers a formula from physics which might be able to be applied to this?
Flux.
Sorry?
Flux.
Flux, exactly. Do you remember the formula?
I remember dust.
Okay. Yeah, I was going to say, so the key thing is that what's going to happen in the next page is going to be sort of a simplified version of that. Because I was going to say there's like versions of Gauss's law that have like, yeah, double integrals in them and stuff like that, which you don't have to worry about, or surface integrals. What? Oh, sorry, that's going to happen second. Never mind. Before I get to the flow and rate and velocity problems, I'm going to deal with something which is called consumer surplus and producer surplus. So this is an economic situation. Again, as I mentioned, sort of there is a bunch of physics stuff. There's also a bunch of other stuff like the population densities, sort of. I don't even know what field that would population studies of some sort. Anyways, the price one is sort of an economics one. Here's another economic situation. So in economics, we represent supply and demand as curves that sort of represent, how much, if you want to sell 100 of these things, what price have you got to charge to make sure there's 100 people willing to buy it? That's called the demand curve. Or if you want to buy 100 of these things, how much do you have to be willing to pay in order to get 100 people willing to sell to you? Right? Those are sort of the supply and demand curves. So if you want to increase the demand, you've got to decrease the price. If you want to increase the supply, if you want to increase the number of people who are willing to sell to you, you've got to increase the price. That's the idea. So usually, I'm just going to draw a picture of this so if this is X, X is always the number of things you want to sell. A demand curve will usually look like this, right? If you don't want to sell anything at all, you can charge whatever price you want. As soon as you want to sell more and more things, you've got to charge less and less of a price in order to actually sell them. A supply curve will usually look like this. If you only want to buy one of these things, you can buy one of them for really cheap. But if you want to buy 20 of them, you need to find 20 different suppliers, so you're going to have to pay more. That's the idea. And this place where they intersect is called the equilibrium point. It's important in economics. I'm not going to worry too much about where that intersects for now. But what I'm going to talk about is what happens. Let's say we want to, we're going to sell this many things. So if we want to sell this many things, all these people here, right? This is a person who's willing to pay this much for the object. This is a person who's willing to pay this much. This is a person who's willing to pay this much, etc. And the idea is all these people here are saving money if they're only paying this price for the thing that you're selling. So if we look at the demand curve, right? This is like 100 people. If you want to sell 100 of your product, there's 100 people who are willing to buy it at this price or above. But these people here are actually saving money. And so what we want to measure is how much money are those people saving in total. This thing is called the consumer surplus. It's called consumer surplus because it's the consumers who are saving money. Similarly, if you're buying 100 of something, and there's 100 different producers who are each selling to you, so say you're buying trees, You find 100 people who are willing to sell their trees to you. And this person's willing to sell their tree for really cheap because they want it gone. This person, however, needs to charge this much for their tree. So all these people are making a profit. Right? All these people down here are getting more for the tree than they actually need to. And that amount the profit that they're making is called the producer surplus. That's the idea. So producer surplus is how much extra profit the producers are making, people who are selling you the trees are making, and the consumer surplus is how much savings the people who are buying your product are making. And we can think of these things, a supply function or demand function, as price depending upon quantity. We oftentimes write supply function as PS and demand function as PD. And if we're selling them for a price of P, so P measures the price we're selling for, we want to be able to measure, okay, what's the consumer surplus, what's the producer surplus? Well, each producer is saving this much, right? They're getting paid P. They'd be willing to sell it for PS. They'd be willing to sell it for this thing on the supply curve. So what you're measuring is this height here. That's the amount of savings that producer's making. This is the amount of savings that producer's making. This is the amount of savings that producer's making. This is the amount of savings that producer's making. And each of these things can be drawn as a rectangle. And the idea is that this producer surplus is actually a Riemann sum. It's actually a sum that looks like this. Similarly, if you want to measure consumer surplus, this is how much this guy's saving. This is how much this guy's saving. This is how much this guy's saving. And if we turn all those things into rectangles, we get a Riemann sum for the consumer surplus. So if we want to evaluate those things, because they're Riemann sums, we can evaluate them using integrals. And the integrals are going to look like this. The integral from 0 to n p minus ps of x. This is the producer surplus, because it's using the supply curve. This is the consumer surplus, because it's using the demand curve. These two formulas are going to be on your formula sheet. So as long as you understand what the letters represent, understanding where these formulas come from is not particularly important, which is why I'm kind of glossing over that. But you should be able to actually use those formulas to compute, let's say, what the consumer surplus is going to be if you have a certain demand function. So the idea in example 7 here is they ask you to measure consumer surplus. Consumer surplus is the integral from 0 to n p d of x minus p dx. It's supposed to be an S, but S doesn't look very S-like. Consumer surplus. So the idea is, now they tell you that the sales level is 300. The sales level is how many things you're selling. So telling you that the n is 300. They've told you what the demand function is. So the PD of x is 20 minus 0.05x. Right, that's what the sales function is. The other thing we need to know is the P. What price are we going to have to charge in order to sell 300 of these things? Well, to find the P, we're just going to plug the 300 into the demand function. Oh, sorry, it's a lowercase d. So we take the 300, we plug it into the demand function. That gives you 20 minus 0.05 times 300. 0.05 times 300 is 15, which is 5. So we're charging $5 an item. So we want to evaluate this integral. This is going to become an integral from 0 to 300. PD of x is 20 minus 0.05x. P is 50, or P is 5. Boy, that whole thing dx. Let me. 20 minus 0.05x minus 5 dx. 20 minus 5 is 15. So we're integrating 15 minus 0.05x. Integrating 15 gives you 15x. Integrating 0.05x is 0.05x squared over 2. this whole thing's got to go from 0 to 300. I'm just going to finish it over here. So if we plug in 300, we get 15 times 300 minus 0.05 times 300 squared over 2. And if we plug in 0, both those things are going to be 0. So if we plug in 0, we get 0 minus 0. And from here on out, it's just calculator work. So you've got to do 15 times 300. $4,500. So 300 squared and 0.05 divided by 2, 2250, which gives you 2250. So what that means, that the consumer surplus is 2250, is all in all, these 300 people who are buying your product together, they're saving over $2,000. That's the idea. That's what that thing represents. Any questions about this one? Okay. So the last type of problem is the one that I sort of mentioned before, where we deal with velocity and flow rate. And the simple physics formula that we use to deal with these situations, again, velocity is how fast a fluid is moving. The flow rate is how many liters are moving per second. Right? They're related to each other. Of course, the faster it is moving, the more liters per second there's going to be. But they're not exactly the same thing. And the relationship is that the flow rate is the velocity times the area the thing is flowing through. So if you've got something traveling through a narrow pipe, it's not going to have as high a flow rate as it is through a wide pipe. That's the idea. So that's the basic physics formula that allows you to calculate flow rates or fluxes. And the idea is we can approximate this thing in an integral and therefore evaluate it with, approximate with a Riemann sum and therefore evaluate it with an integral. So the idea is where this is going to be important is in situations where the velocity is different in different places. So for example, if you've got a stream of water, oftentimes it doesn't flow as fast at the bottom of the stream as it does at the top. It also doesn't flow as fast near the edges as it does in the middle. But let's just say it's just height, right? The idea is you can cut this stream into slices. You can find the velocity in this strip. The velocity can be a function of x, which maybe is measured down from the top of the stream. So you find the velocity in that strip. So you cut it up into strips. And the velocity in that strip, you multiply it by the area of that strip, right? The area is the width times delta x, right? Delta x is that thickness. Multiply the thickness by the width, is the area of a rectangular strip. You can turn this into a Riemann sum, right? So the flow rate is v of x times w of x delta x. So we can turn this into a Riemann sum. Which will look like sum v of x, w of x, delta x, the delta looks not very delta-like, which then will become an integral. V of x, w of x, dx. So the idea is that this procedure can be used to find the flow rates if we know what the velocity is. We take the velocity, divide it up into strips, take the velocity of each strip, multiply by the area of that strip, sum them all together and turn that into an integral. One thing I realized is this formula here, I forgot to put on the formula sheet. So I'm going to add this to the formula sheet before I actually make up the test. So the version of the test is going to have that on there. Okay. So here are some examples. So the first example deals with the velocity of blood in a blood vessel. This is the main example that's done in the textbook. For whatever reason, the textbook does this example, but doesn't do any other velocity examples, which again is one of the reasons I created that extra problem on the handout, is because I'm not going to ask you exactly the same situation as the textbook is. I could ask you another velocity problem to be slightly different. So here is the formula for the flow rate or the velocity in a blood vessel. And again, the velocity is going to be faster in the middle of the blood vessel than it is at the edge. R is the distance is the radius from the middle of the blood vessel. Capital R is the radius of the blood vessel. Now, of course, that formula is not a very nice formula as it stands, which is why in this problem I tell you what a whole bunch of these numbers are. Eta is, this letter is 0.027, capital R is 0.1, L is 50, P is 3,000. So here, the velocity function is going to be 3,000 over 4 times 0.027 times 50. And that whole thing is being multiplied by capital R, which is 0.1 squared minus lowercase r squared. This simplifies to 556 times 0.01 minus r squared. Again, I rounded off this number in front. When you're dealing with word problems like this that have ugly numbers, feel free to round things off. Yeah. Now, the thing to mention is that here, the flow rate depends upon the distance from the center of the blood vessel. So if we're going to try to cut this blood vessel into strips, we can't use horizontal strips or vertical strips because both those things will involve in a strip having different flow rates at different places. This is another one of those situations where I'm going to have to use circular strips. I think earlier this class. I'm going to have to cut it up into pieces that look like this. Now, if you remember, the area of a circular strip is the circumference times the thickness, which is delta r. The circumference is 2 pi r. So the flow rate is the velocity times the area. The velocity is this thing, 556 times 0.01 minus r squared. And the area is 2 pi r delta r. Right, so this is the flow rate on one little strip. If you want to find the flow area of the whole thing, we can turn this into a Riemann sum, turn it into an integral. And the integral will look like 556, 0.01 minus r squared, 2 pi r, but rather than delta r, it'll now become dr. And the limits of integration here, well, we're going to start in the middle of the blood vessel when r is 0. We're going to stop at the edge. Now, the edge is going to be when r is 0.1. And that's because capital R here represents the actual how big the blood vessel is, which is 0.1. If you actually read the way the question, I've cut off some of the wording of the question here to make it fit on the slide. That sort of makes it more clear that capital R represents that distance. But then, yeah. This is the integral we would come up with. There's another one that's complicated enough I wouldn't ask you to actually evaluate this. Just write it out. And that will work. Any questions about this problem? Last example I'm going to do from Chapter 8 deals with water flowing through a stream. And again, I do these exams, I created this extra example, which is not something from the textbook, because I wanted you to be able to see more than one situation of velocity and flow rate, not just the blood flow one. So here's water flowing through a stream. Here this stream has a semicircular cross section. So it's a semicircle. The radius is 1 meter. Right? And the velocity depends upon the depth. So at the depth of x meters, the velocity is 1 minus square root of x. So the velocity as a function of x is 1 minus square root of x. And so we want to find the flow rate. Now here again, we're going to have to figure a way of cutting this strip into slices. Well, what the velocity depends upon is the depth, which means we're going to want to cut it into horizontal slices. We're going to want to cut it into slices at the same depth, because slices at the same depth will have the same velocity. Now, if we want to measure the area, we're going to have to take the area of this strip is going to be the width of the strip, from here to here, times delta x. And the width is that distance there. Now again, as in a lot of these circular situations, we can draw out a right-angled triangle. This distance is 1, this distance is x, and this distance is half of the width, w over 2. So w over 2 squared is 1 squared minus x squared. So w over 2 is square root 1 minus x squared. So w is 2 times the square root 1 minus x squared. So here the area is going to be 2 times the square root 1 minus x squared times delta x. So I have a formula for the velocity. We have a formula for the area. We want to find the flow rate. We've got to multiply those two formulas together. The flow rate is the velocity times the area. So we're going to have 1 minus square root of x times 2 times the square root of 1 minus x squared, delta x. And so we can turn this into an integral. As we turn it into an integral, the delta x becomes a dx. We've got to figure out what the limits of integration are. Well, we're going to start, the top of this thing is going to be when x is 0. The bottom, this is a radius of 1 meter, so it's going to stop when x is 1. So the integral here is going to go from 0 to 1. And again, that integral is going to be a very hard one to do. So this is another example where it says set up, but do not evaluate the integral. You just, in that case, you just go this far, and then you stop. Oh, this is, I don't know why I have example blank. This is example blank. Anyways. Any questions about this example? Okay. Well, that's sort of what we're going to cover in Chapter 8. And again, there's a few selected topics. There was sort of a whole bunch of topics. One thing I'm going to mention is that, all the formulas you'll need will be on the formula sheet. So the key thing here to understand is the process of going from a formula, like f equals v times a, to an integral, right? That process is the key thing here. What else was I going to mention before I stop? Oh yeah, so I've got some group problems I'm going to give you. Again, please work on those for the rest of class today and let me know how you're doing. Ask me questions, that sort of thing. Talk to your groups. The other thing to mention is I want you to take a look at the formula sheet I've handed out and make sure there isn't anything else I forgot to put on there. Because again, I forgot to put the f equals VA on there. Just if you can go have a quick look at it and see if there's anything else you think I forgot to put on there. And I'll let you know if there's a reason specifically I didn't put it on there. Like I didn't put on the area of a circle, the area of a rectangle, the area of a triangle, because at this point you should know those. I didn't put on volume of a cylinder because like the area times the height. Again, that's something you should know as well. But there might be other things that I should have put on there and I didn't. Yeah, anyway, so let me show up those group problems and start working on them, and I'll answer questions about the formula sheet as this is happening.
Of the new formulas that we've learned, what would you expect us to remember?